It is a great pleasure for me to introduce our speaker today, Matt Kahle. He will be talking about configuration spaces of particles. So please go ahead, Matt.
Thanks, Jesus. Thanks to the organizers of the seminar for the invitation and the opportunity to speak. And thanks everyone for coming today. And I just want to say it actually feels special. And I appreciate the opportunity to give a talk in these kind of strange times and challenging times. And I miss seeing everyone in person at conferences, but it's important that even while we're waiting for things to get better with the pandemic, that we still get a chance to meet from time to time and share our ideas and see each other's faces even. So with all that said, I really encourage you to interrupt me during the talk and ask questions if you have them. I would appreciate it. And it also makes me feel like I'm not just talking into the void or something if you interrupt me with questions. So it's good for all of us. Okay, so I want to talk about configuration spaces of particles today. And this is joint work with a number of people who I'll acknowledge as we go along. But let me just remind you of a little background. Let's see. So the background inspiration would be configuration spaces of points in the plane, although configuration spaces of points are of course studied much more generally. We could talk about, say, points on a manifold or in other spaces as well. So given this audience, I think this will be a very quick review. I just want to remind you some of the basic properties of configuration spaces of points in the plane and just what is the configuration space of points in the plane. So, so it's a subset of R2n. This is the ordered configuration space of n points in the plane. It's a subset of R2n, and it's just, you put your endpoints down in R2, but the restriction is they have to be distinct points. So xi is not yi is not equal to xj, yj, whenever I is not equal to j. So this is some, open submanifold of R2n. It's called the ordered configuration space of points. This is what I'm trying to illustrate here is just one point in that configuration space. We could also talk about the unordered configuration space, which is closely related, and it's the quotient of this space by the natural Sn action. It's a nice action of the symmetric group that permutes the points. In particular, it's free, and so the quotient is still an open manifold, and so on. Okay, so I think it's kind of fair to say that the configuration space of points in the plane is like more or less completely understood. Like, the topological invariants we might be interested in are seem to be all be well studied. So first of all, the homology of the configuration space of points in the plane. I won't keep saying ordered configuration space. I just, throughout today's talk, I'll just be talking about ordered configuration spaces, but you could ask similar questions to what we'll study for unordered configuration spaces. And in some ways, it may be even more natural. But so for the ordered configuration space of points in the plane, homology is free. There's no torsion in homology. So if I tell you the Betti numbers, then I've told you everything about homology with integer coefficients. And these are the Betti numbers. This is the Poincare polynomial for the configuration space of points in the plane. If we want to know the Betti numbers, then we can just multiply these polynomials. I think this was first proved by Arnold. These factors, by the way, they have, topological meaning. So first of all, the configuration space of 2 points in the plane is easily seen to be homotopy equivalent to a circle, because, by translation, 1 point we could assume without loss of generality is the origin, and then So it's like the other point has to be anywhere else. And so it's like the punctured plane, which is homotopy equivalent to the circle. So the Betti numbers of the circle or the punctured plane are, 1 in degree 0 and 1 in degree 1. But then, there's a map from the configuration space of 3 points in the plane to the configuration space of 2 points in the plane, where you just delete the third point. And that's a nice map. That's a fibration. The fibers all look like the twice punctured plane, and that's the Betti numbers. And so, by writing it as an iterated fibration, there's a spectral sequence calculation that computes all the homology. Okay, so that's the homology, but another nice feature of the configuration space of points in the plane is that it's a k pi 1. So all the higher homotopy groups are 0. Pi 1 is non-zero, but pi 2 and higher. So an equivalent way to say this is that it's an aspherical space. It has a contractible universal cover. So if you've never really thought about configuration spaces before, you could think of this as like something like a torus or something, where the cover, the universal cover of the n-dimensional torus is n-dimensional Euclidean space. But this is somehow like a twisted version of the torus or something. Okay, and then so everything, if it's a k pi 1, everything comes down to pi 1, and that's what's sometimes called the pure braid group, and that's very well studied. So so this is a manifold that we know lots of things about. Maybe surprisingly, though, even though it's been studied for decades, people have continued to discover new things about it. So, a hot topic over the last several years has been representation stability. I'm not going to get into this today, but it's the basic idea is that, there's this SN action on the space. Well, then that induces an SN action on homology. And what people have discovered is that, there's some surprising connections between the SN action on homology of the configuration space of endpoints and the SN plus 1 action on homology for the configuration space of n plus 1 points. And so there's something about the representation stability on homology stabilizes. A number of people have worked on this. So even though it's fairly well understood, there do continue to be new things discovered about the configuration space of points. Okay, so now we want to sort of consider a different framework. We want to modify the picture a little bit. Instead of considering points in the plane, we want to give the points thickness. So we'll think of them as disks, and then we want to put them in some kind of bounded region. So the example that we might be interested in would be disks in a box. So here we'll denote config in R means the configuration space of n disks of radius R and the unit square. And the disks aren't allowed to overlap except, possibly at their boundaries. So you can define this a couple of different ways. So, one is you don't allow the disks to touch at all, so that the inequalities, we just have to keep track of the centers of the disks. So this is a subspace of the configuration space of endpoints in the plane. First of all the points have to be in unit square, but then the disks of radius R are not supposed to overlap. So we could write that down with open inequalities or closed inequalities. Is it strict, like less than, or greater than, the distance between them has to be strictly greater than, or is it just greater than or equal to? And there's advantages of each. I won't really get into this today, but like the advantage of greater than, strictly greater than, is that this is then an open submanifold and it's still a manifold. But one advantage of having greater than or equal to is that, well, for one, the space is compact, and that's often convenient in topology. And that's when Peter Bubenik and Yuli Baryshnikov and I studied these spaces. We had some other reasons why it's sort of nice to consider the closed configuration space of n disks of radius R. But this is just sort of like a In a sense, it doesn't matter very much, because if you take the closed configuration space, there exists a little open configuration space that deformation retracts back down onto it. So up to homotopy equivalence, if you consider all of the spaces, you're considering the kind of same class of spaces. Okay, so here's a typical point in the configuration space when, n equals 10 and r equals something, 0.083, I guess. Here's one of our inspirations for this question, and a nice quote from Giancarlo Rota. He says, what if we have a bunch of pennies and we drop them onto a rectangular carpet? What's the probability that none of them overlap? No pair of pennies overlaps. It's interesting where this comes from. This is an undergraduate text on probability theory that Rota wrote, and I think was never published. I think he just kind of kept writing and rewriting this undergrad textbook, and it was still in progress when he passed away. And you can find like a PDF of it, online if you search for it. And it seemed very beautiful. And I kind of wish it was a published textbook that we could use to teach undergrad course. So he says something very provocative here, Rhoda does. He says that if we knew the probability that no pair of pennies overlapped, we would know why water boils at 100 degrees. So, what could he possibly be getting at here? But, by the way, I gave this talk one time, and Mark Goreski was in the audience, and he said, we know why water boils at 100 degrees. That's the definition of 100 degrees. And, Goreski has a good point. So, but what does Rhoda mean? Well, what he's really talking about is what's the volume of the configuration space of disks in a box, right? So the probability that no pair of disks overlaps is it's the volume of the configuration space of disks in the box divided by the configuration space of points in the box, right? So, and the volume of the configuration space of points in the box is just one. It's the 2 n-dimensional cube, and with side lengths 1, so its volume still 1. So the thing we don't know is the volume of the configuration space of disks, and what physicists think happens. So like fix n, say, the number of disks, and let r, your radius, vary. It seems that at some value of r, the volume drops off very, very suddenly. That's what they sort of find in some sense, kind of indirectly, but from experiments, computational experiments. The volume drops off very suddenly at some radius. And so better than radius, a better way to think of it would be at some density, like at what, so when the disks take up, 70% of the area of the box, the behavior seems to be different than if the disks take up 72% of the area. And so what do we mean by the behavior is different? Well, like loosely speaking, the disks start to kind of lock up. If you take a typical point in the configuration space, the angles that the disks take are getting close to pi thirds and so on. And they can measure this. So they measure it by sampling a random point in the configuration space. And then from that random point, they measure it. Various invariants. So really a more accurate thing to say would be like, how well are the angles at this disk with the neighboring disks correlated with the angles of this disk with its neighboring disks? How fast does that correlation fall off with distance? And there seems to be some phase transition at around when the disks take up about 71% of the area of the box. And there's no mathematical explanation for this. There's not even a heuristic, as far as I understand, but that, so by the way, you can compare that to the close packing density. Like that's when the maximally dense packing of disks in the plane is more like pi over square root of 12. It's like 0.9069. So it's far away from, the densest possible packing of about 91% of the area of the square at about 71% of the area of the square. Things, something shifts. And that to physicists, this is an analog of a liquid solid phase transition. So they say that once the disks take up more area than 71%, then it's like the system has gone into like a solid state, essentially. It's like they're freezing. So this kind of makes some kind of physical sense. Hard sphere systems to physicists are said to be athermal. We don't have a parameter that's the analog of temperature, really, but I'm talking about the size of the disks. That's a stand-in for pressure, right? Rather than increase the size of the disks, you might find it more physically meaningful to squeeze in the size of the box. Mathematically, this is the same configuration space, but to physically, that squeezing in the size of the box is something like pressure. So we only have kind of in some sense, a one parameter system here with pressure as our parameter, but then there's like something like a liquid solid phase transition. Pretty amazing that they see that with experiments, because this is the simplest model of matter you can imagine. Like your atoms are just disks. They're all the same size. And the only force is the repulsive force that says, it's not even like a force you write down like F equals ma or something. It's a force, it's in the sense that there's an energy potential that says that the energy of the system is infinity if any pair of disks overlap, and it's zero otherwise. So just with a system as simple as that, it's expected to go through a phase transition. So, this is the sort of thing that we'd like to understand. I pulled this, I can't remember where I found it, just some Google image search, I guess. But it's kind of funny that, this is a typical phase portrait. There you would have two parameters, typically pressure and temperature. Although if you look around, you can find other kinds of phase portraits where one of the parameters is like entropy or something else related. It doesn't always have to be pressure and temperature. But it's funny that it says, although this is a generic phase diagram, it's funny that this one I found says that it's water, because the actual phase portrait for water is a bit more complicated than this. If you've ever really looked at it, that there's something like a dozen different stable states of water. And I don't know if any of you have ever read Kurt Vonnegut. Which one is it? Cat's Cradle? Ice Nine. Like that's based in like real physics, that there are, if you get, superheat water and then cool it, or, that different things happen. And the premise of this Kurt Vonnegut novel is like a form of water that can solidify, but at room temperature. Like, it can crystallize. And once you have a crystal like this, if you drop it in a glass of water, it makes the whole glass of water crystallize. So anyway, we would like to understand this sort of thing, especially from a point of view of geometry or topology. And to me, the dream would be, okay, maybe the volume of that configuration space does really drop off very quickly. And topology isn't necessarily good at detecting things like volume, right? That's not a homotopy invariant. But what if the reason the volume is dropping off is that there's lots of little holes in the space, and those holes are eating up the volume? Then you might be able to detect it with something coarse, like even like Betti numbers, or a rough approximation to the Betti numbers. And to me, that seems much more likely, that there's lots of little holes that are appearing in the space as you vary the radius, than that there's like one big hole that's eating up all the volume. That somehow doesn't seem very geometrically likely. So that's just sort of like one motivation to study the topology of these spaces. I mean, honestly, I think it's just mathematically appealing to study the topology of configuration spaces of particles, but there is this kind of physical motivation. So here's some pictures. I think these pictures were done by Werner Krauth, who's like one of the real experts on the computational statistical physics side. And here's a typical configuration where they take up 48% of the area of the box, and here 72%. And it already kind of starts to look like a crystal, where many of the angles of the disks nearby are, seem like they're close to pi thirds. So, okay. So here's another, just kind of neat quote that I found. Percy was the one who got me interested in this. Some time ago when I was his postdoc. I worked with Percy and Gunnar when I was a postdoc at Stanford. So around that time, Percy had a bulletin of the AMS article on Markov chain Monte Carlo revolution, and talking about Markov chain methods, and especially in applications in science. And one section of that survey article is devoted to disks in a box. So this is how you get a random configuration space, a random configuration of disks in the box. Is you put the disks down in the box in some arbitrary starting configuration, let's say where their centers are on a lattice or just something that's convenient, and then you wiggle the disks around randomly. So a little bit more precisely, choose one of the n disks uniform randomly, so every disk has equal probability, and then perturb it within a little epsilon disk, centered at its center, just epsilon small, just try to wiggle the disk randomly, that one disk. So if that results in the disk overlapping with one of its neighbors, or the disk going out of bounds if you have boundary conditions. I mean, they study this sometimes in a square, but they sometimes like to study it on a torus or something too, so there's no boundary. Then if it results in a disk going out of bounds or an overlap, then you reject the move. And if it's a legitimate configuration that you could get to that way, then you accept the move. So this is a very simple Markov chain, but it's been studied a lot. And yeah, this is a special case of the metropolis algorithm. And so one of Percy's interests in this is that from sort of basic principles, this should converge to the configuration under mild assumptions. This should converge to the configuration space of disks, the uniform distribution on the configuration space of disks. But the mild assumptions include things like that the configuration space is actually connected. And even that kind of thing is not known. Like, how small do you have to make R to make the configuration space of n disks of radius R in a unit square? Let me just advertise that as an open problem. Like, we know certainly it suffices to take R less than like 1 over n or something. Like if in the limit the disks only have length and don't have area, like they can only go along one side of the box, then definitely the configuration space is connected. You can show that. On the other hand, like if there's some big enough positive fraction of the box, then they can definitely get locked up and stuck. So but we don't even know what's the right order of magnitude, more like R close to 1 over square root of n, or close to R close to 1 over n, but like what's the right exponent on the n? So but that's part of Percy's interest, is like, when is the space connected? Because to have talk about things like mixing time of Markov chains, you'd at least like to know that it's connected. But then he suggests studying what are the Betty numbers and so on also. So here's a few references for hard disks in a box. Percy's article is a nice place to start, and it's a fun article to read in general, a nice survey on Monte Carlo sampling methods. And then I wrote a paper about how the disks can get stuck in a box if you're only allowed to move one disk at a time. This is even for pretty sparse, like R close to 1 over n. Let's say for some bigger constant, R constant over n. So the disks again only have length in the limit and don't have area. They can still get stuck in a box. So it's but it's not a disconnected configuration space, because the sense in which they're stuck is only locally jammed. They're stuck if you can only move one disk at a time, but if you're allowed to move multiple disks, then you can move them with collective motions, or and they're sort of barely stuck. We're just checking that they're stuck and that the angles, if 3 disks touch it and all the angles are less than pi, then you can't move this disk. But if that angle is very, very close to pi, then, which they of course are, then physically it might not have much meaning. So, okay, so another earlier paper was with Gunnar Carlson, Jackson Gorham, and Jeremy Mason. We studied, the configuration space of disks in a box. And so these two papers kind of go together. Let me say something about the one with Brishnikov and Bubenik first. We talked about a kind of Morse theory for these configuration spaces and pointed out that the only time that if you vary R and fix N, these spaces are all kind of nested in each other. And the only time the topology of the configuration changes, at least up to homotopy type, is in the presence of kind of jammed configurations. A better word is like mechanically balanced. So like one example, something that you might not call jammed, but you would call mechanically balanced, is like a row of disks goes from one side of the square to the other. Then you can put forces on the edges so that they cancel out at every vertex, at every disk center. So one of the corollaries of our main theorem in this paper is like, that's the last time the topology changes, because that's the smallest mechanically balanced configuration. So if the disks are smaller than that, then the configuration space of disks is homotopy equivalent to the configuration space of points. But the more general statement is the homotopy type can only change in the presence of these mechanically balanced configurations. So then in this paper, experimentally, we find lots of mechanically balanced configurations for up to, I'm embarrassed to say this, but like 5 disks in a square, not very many. And already the hint, we didn't prove anything in this paper, it's in a physics journal, but the hint is that the topology changes dozens of times, even for a system that small, 5 disks in a box. So we're getting hints that the topology can be quite complicated. So to me, that's actually good news and bad news. The bad news is maybe the topology is hard to understand and we should just try to study it approximately. But the good news is the topology seems rich and maybe it can actually capture something statistically, mechanically interesting. Okay, so we're not going to talk much about disks in a box today. That's just kind of the motivating example. But the truth is we don't know very much about the topology of configuration space of disks in a box. It would be nice, for example, to have a better Morse theory. This min-type Morse theory, we just say so far, these are the critical points where the topology can change. But in real Morse theory, like smooth Morse theory, a lot more than that. Like how the topology changes, like you're attaching a cell whose dimension equals the index of the critical point. Analogs of theorems like that could be really, really cool. So there's a lot to do in this area. So what I want to tell you about now is, instead of doing disks in a box, what about disks in an infinite strip? So just imagine, like 2 horizontal lines in the plane, and the disks have to stay between them, 2 parallel lines. So this is somehow, it's easier to study than disks in a box, but it's still more complicated than points in the plane, and it's somehow, it seems like topologically interesting. So this is a good, toy problem to work on. Is like, it's interesting enough that something might happen, but but easy enough that we can prove some things about it. So there's a typical point in the configuration space. So now I'll just use C for the configuration space of n disks, and we'll say the disks have unit diameter. I know it's our habit in math that disks are always unit radius, right? But here they're unit diameter because I want to say the width of the strip is measured in terms of number of disks. So the width of the strip is W, and so the disks are unit diameter. So really, like, the width could be any real number, but one of the things we prove is that the homotopy type only changes like at integer numbers of disks. So, if the strip is 3.3 disks wide, it's the same as 3.4 disks wide. But when it changes is when you get to 4 disks wide, and that means 4 disks can get past each other. Okay. So let me tell you some results. So the first theorem, and maybe our main theorem, was just to approximate the Betti numbers. So J is always the degree of homology we're looking at, and W is always the width of the strip, and N is always the number of disks. So this is kind of a nice, it seems like a reasonable thing to look at. Fix the homology you're looking at, the homology group you're looking at, fix the width of the strip, and now let the number of particles go to infinity. And because it's infinite in this direction, we don't even have to renormalize, as n goes to infinity. The disk, there's always room for more disks. Okay, so this is, hard to read. Let me just say what to notice here. For some conditions on W and J, we get an isomorphism on homology, and homology of configuration space of disks in the strip coincides with configuration of endpoints in the plane. And then we know what the homology of the configuration space of endpoints in the plane is. We had that on the first or second slide of the talk. It's, we had the Poincare polynomial. From that Poincare polynomial, you can extract a formula for the jth Betti number of endpoints in the plane. And if you fix J, then it's a polynomial of degree 2J. And so, the rough rate of growth is n to the 2J. But what's really interesting is for some other range of parameters, the homology grows exponentially fast. So, so for some J and W, whatever conditions it are, and I'll show you a picture in a minute of sort of the parameter space, the jth Betti number, so again, J and W are fixed, n's going to infinity. So what to see here is there's an exponential part. Q plus 1 to the n is growing exponentially fast. And then there's also a polynomial part. And this big theta notation means this is the right answer up to a constant factor. So there's an upper bound, that's some constant times this, and there's a lower bound that's some other constant times this, that, those hold for all sufficiently large n. So I think of this as sort of the first order asymptotics, and this as sort of the second order asymptotics. So this was surprising to us that we didn't know what the answer was going to be, or if we could even say anything about homology for large n. But the fact that it's growing exponentially fast instead of polynomially fast is interesting and exciting to us, that the homology of these spaces can be really complicated, that there can be lots of homology. Yeah, and so this Q and R have, are in terms of J and W. So J and W are fixed, so then Q and R are also fixed. And this range of parameter, homology grows exponentially fast. And then finally, there, under some conditions that seem sort of trivial, like if the width of the strip is 0, or if the width of the strip is 1 and J is greater than or equal to 1, then homology is trivial. Okay. So, but here's a summary of like that main theorem. This is really just trying to summarize what happens when J is fixed and W is fixed and when n goes to infinity. So this is the rate of growth of the Betti numbers in that case. So for example, if the width of the strip is 3 and we're looking at Betti 5, it grows roughly like 3 to the n to the 8th, and that's right up to a constant factor. So that's the rate of growth. But now as we're going horizontally, we're increasing the width of the strip, and right here at this point, it just agrees with the configuration space of points in the plane, and so it just stays. So I'm writing into the 12th here, but it's actually a polynomial of degree 12 that we could write down exactly. It's the configuration space of points in the plane. So, so the bold ones are sort of the interesting homology groups. And then the lower, the not bolded ones, these are just agreeing with the configuration space of points in the plane. And then out here, we have some trivial homology. If the strip isn't even wide enough to accommodate non-trivial homology. So this suggests a metaphor. So let's call it the homological gas regime. If the inclusion map from your configuration space of particles into the ambient configuration space of points induces an isomorphism on homology. And that's totally reasonable, right? Because an ideal gas is one that physicists say where the particles are acting like points. So as topologists were saying, okay, through the lens of that homology group, if you get an isomorphism on homology, if the particles are acting like points, then it's a gas, at least for that homology group. So a homological solid regime, I think also kind of makes sense. The crystal regime or the solid regime for, configuration space, we shouldn't expect that there's like really interesting topology. That the atoms are sort of starting to get locked into place and they can't move around a lot. There's not much freedom. So we'll call that the solid regime. And then we'll say, the homological liquid regime is everything else. So this is a working metaphor, and there's other definitions that are possible here and that could be more refined, but I like this as sort of a first pass. So once we had those definitions, then it suggests revisiting our main theorem, because those definitions make sense even without it. At first it kind of seemed like maybe homological liquid regime is Betty numbers grow exponentially, and homological gas regime is they grow polynomially fast. I mean, something like that could be reasonable, but we just have an isomorphism on homology that's much stronger than they grow. That tells you everything about how fast they grow. But that question of is there an isomorphism on homology or not, that makes sense for every fixed n, and not just if n is going to infinity. So this theorem is not asymptotic. The second theorem, this is just what happens for like n equals 5 or n equals 10. I think that's the wrong slide. Yeah, I redid that slide. I just didn't delete the copy. So for some rate conditions on W, J, and N, homology is 0. For some conditions on W, J, and N, homology is non-zero. And then for some conditions on J and W, we get an isomorphism on homology. So let me show you a summary of this. So we can't compute, at least so far, we can't compute homology for up to n equals 24. It's way too big for computations. I'll give you some sense of how big things are getting even for smaller n in a second. But that theorem tells us, if J and W, so we fixed n, so our other parameters are J, the degree of homology, and W, the width of the strip. For this choice of J and W, we get an isomorphism on homology. For this choice of J and W, homology is trivial. So remember when we had the asymptotic picture, we only saw that these were 0. But if you look at the whole picture for a fixed n, there's a bunch more non-trivial homology groups up here that's sort of an interesting shape, and that this is asymptotically some hyperbola. So the homology is trivial out here. And then in between, is everything else. And we expect the Betty numbers here to be huge compared to out here for the most part, So that's, our kind of phase portrait. And, width is clearly some kind of stand-in for like pressure or inverse pressure or something like that. And I don't know what degree of homology means, I don't think it's the same as degree in temperature, but it's like we're doing a phase portrait, right? We have two parameters and we're seeing qualitatively different topological behaviors as we vary those parameters. So let me just tell you something about the idea of our proof of the theorem and then move on to another topic. So for lower bounds on Betty numbers, we want to produce a lot of homology. So we use duality between homology, singular homology, and Borel-Moore homology, or homology with closed supports. And then, some intersection theory to characterize they're non-trivial and that they're linearly independent. So, we have, we have a cell complex that I should reorder these slides. We have a cell complex that gives us the homotopy type of the configuration space of disks in a strip, and it's a subcomplex of the Salvetti complex for the braid group. That's well studied. It still takes several pages in our paper to prove that we have a homotopy equivalence between our configuration space of disks and this subcomplex of the Salvetti complex, but then the cells of the Salvetti complex are indexed by these kinds of, they're like permutations. So I have 23 disks and this configuration space. And so I can take a permutation of 23 elements, but then I can also drop kind of bars in between them. So this is one of my symbols that indexes cells in our cell complex, but it's also going to index some non-trivial cycles. So let me just show you what the cycles are that are indexed by this symbol. So this is a 12-dimensional cycle in singular homology. So what's happening is like these 5 disks are orbiting around each other. This is a typical kind of thing you do for configuration space of points is you make these toruses. So 23 and 6 orbit around each other, but then that little Earth moon system orbits around the sun, 11, and then so we can choose 4 angles freely for these 5 disks. We'll always make sure these 2 disks are tangent to each other. Then the disk that they sit inside is always tangent to this disk. And then the disk that contains those 3 disks is always tangent to this one, and that is just tangent to this. So I can choose 4 angles freely. And so I have a 4-dimensional torus representing all possible places to put those disks. Another 4-dimensional torus, 1-dimensional torus, 1-dimensional torus, 1-dimensional torus. So in all, it's a 12-dimensional torus if I allow all possible choices of angles here inside this 46-dimensional configuration space. And then here's a point in 34-dimensional, it's a 34-dimensional cycle in Borel-Moore homology. So like these have to stay in the same, they have the same x coordinate. These have the same x coordinate, so do these, but they can, there's actually a little bit of room here for them to bounce. They have the same x coordinate and they have to stay in order, but they can move freely within that. Their y coordinates are free to choose as long as they don't touch or go out of bounds. So out of the 46 dimensions, we've knocked off 1, 2, 3, 4 dimensions, and then another 4 for that because they all have to be in the same, they have the same x coordinate and these have the same x coordinate. So now it's codimension 12. So this is a 34-dimensional cycle in Borel-Moore homology. And then this 12-dimensional cycle in singular homology and this 34-dimensional cycle in Borel-Moore homology intersect at a single point, and the intersection is transverse. So by controlling the combinatorics of what are all the different symbols indexing all these cycles, we can show that they don't intersect unless they're indexed by the same symbol. And then if they are indexed by the same symbol, they intersect transversely at a point. So then we get that all these cycles are linearly independent. So that's how we get lower bounds on Betti numbers. So for upper bounds on Betti numbers, we use the cell complex and we do discrete Morse theory on the cell complex. And here's a picture of the Salvetti complex for 3 points in the plane. And, our subcomplex is like, in the case of 3 particles in a strip of width 2, it would just be this subposet, the subcomplex. But yeah, that's the most technical part of the article is the discrete Morse theory on this cell complex that we have. That's a subcomplex of the Salvetti complex. But then the discrete Morse theory, just analyzing the number of critical cells of that discrete gradient vector field gives us an upper bound on the Betti numbers. And then somehow miraculously, the upper bound almost matches the lower bound, or they match up to a constant factor.
Can I ask a quick question?
Yeah, please.
Do you have a geometric interpretation for the quotient complex?
What do you mean the quotient complex?
Of the Salvetti complex by the subcomplex you're studying?
I don't. You're saying quotient the Salvetti complex itself by this subcomplex?
Yeah.
And is there a nice way to think of that? There might be. I've just never thought of it before.
I just wonder because then there's a long exact sequence in homology.
I see. Okay, that's a reasonable question. Right. So my advisor's advisor's advisor was Bott, and I sometimes think of myself as a fourth generation Morse theorist. Okay, so because we have a cell complex, though, we can also do calculations for small n, exact calculations. So we have a table in our paper, and like we do all the n up to 8. Here it is just for n equals to 8, and here's the Betty numbers. By this point, though, the cell complex is getting up to millions of faces. We might be getting close to 10 million faces in the cell complex. So this is as far as we are able to go. But let me just advertise, there's some recent work in progress by Hannah Alpert and Fedja Manin. They don't have a preprint up yet, but I've been talking with them about it. So I'm not a collaborator on this. This is their work. But they can actually describe an integral basis for homology. They actually have a lot more than this. They have a sort of twisted algebra structure that completely describes, you can put fixed W and look at the configuration space of n disks and a strip of width W, but then allow all the different n at once. You can put all those, homologies into one algebra structure that they describe. It's finally generated non-commutative twisted algebra. And then they have all these beautiful consequences. So for example, if you want to fix in and let W vary now and look at persistent homology, they can compute it. And this completely circumvents the cell complex that Bob and Hannah and I had talked about. So they can go much larger. So here is n equals 12. This is a little piece of the persistent homology when n equals 12 disks, and this is the width of the strip. The width of the strip goes from 0 up to 12, but then once it's wider than 12, you're into the configuration space of points in the plane. So we may as well say infinite here. These are the bars in the barcode, and this is the multiplicities of the bars out here, and these are exact. So these might be some of the most complicated barcodes ever computed. I'm not sure, but they're it's really beautiful to look at. And there's lots of neat corollaries, like a bar in the barcode, if it's born by time W or by width W, it either disappears by width 2W or it persists forever. So like cycles that are born by width 3, they disappear by width 6, or they're in, the configuration space of points in the plane. And, time 4, they can persist all the way to time 8, but then that's it. So there's lots of neat things in here. And I'm looking forward to their preprint being out. Oh yeah, so that's one thing, is that if you fix n and vary W, they can say something about persistent homology, but also if you fix W and vary n, they can say something about representation stability, like a generalized representation stability for homology of these things, but it seems kind of remarkable. So, okay, so in the remaining few minutes, let me tell you about hard squares in a rectangle. We have a preprint up on the archive on this also, if you're interested. So, it's exactly what it sounds like. Now we're going to we want to go back to a bounded region. Maybe disks in a strip is too easy. Like if we're bounded in this direction, but not bounded at all in this direction. What if we put them back in a bounded region like a square, but we make our lives easier by taking L infinity disks, making our disks little squares. So this is like the 15 puzzle. That's the case, P equals Q equals 4 and N equals 15. And, this is a picture from the 19th century. I think this is Sam Lloyd. Mathematicians had already observed in like 1870s that there's no sequence of moves that switches 14 and 15, but that's actually a topological observation, right? That the real observation is that the Betty 0 of the configuration space of 15 disks and of 15 squares and a 4x4 square is 2. There's 2 different connected components. Okay, well, what about higher homology? Well, we can show things like, that's probably known for 150 years that there's 2 connected components, but we can show, like, we actually have a formula for what Betty 1 is, because we get a cell complex here. So we have a cubical cell complex that captures the homotopy type of this configuration space. So what about if we have like 6 squares in a 4x4 grid, for example? Well, here's one of the tables from our paper. So there's the homology for 6 squares in a 4x4 grid, and there is higher homology. So here's another view of the homology of these spaces that might be interesting to look at. Like so yeah, part of the problem now is we have 4 parameters: n, the number of squares; j, which homology we're looking at; and p and q, the sides of the rectangle that they're moving in. So it's hard to visualize the data even, right? Because it's sort of 4-dimensional. But here's another view that I think is a nice one. Fix the number of squares and fix the homology you're looking at, and now let the sides of the rectangle vary. And this is there's actually maps, right? There's maps going to the right and there's maps going up. The configuration space of squares in a 3x3 square lives inside, and a 3x4 rectangle lives inside a 4x4 rectangle. So we have maps to the right and maps up. And then, now this is the gas regime. Once things are big enough, the homology stabilizes. And this is the solid regime where the Betti numbers are 0. And in between, we have what we call the liquid regime. And outside of this box, things are stable. You could say they're stable altogether this way, and then they're like stable in one direction here. At that point, you're back to disks in a strip, like hard squares in a square. If you fix one dimension and let the rectangle grow in the other direction, it's homotopy equivalent to disks in a strip. That's not hard to check. So, but here's one of the questions that we're left with in our paper that I think is really neat. This slide kind of summarizes our main results as well as our main conjecture from our paper. So given NJPQ, what are necessary and sufficient conditions on NJPQ just for homology to be non-trivial? We don't know, but we proved that homology, if there's non-trivial, it's under this, it's inside this trapezoid. We know y has to be less than or equal to 1 minus x. We know y is less than or equal to x, and y is less than or equal to 1/3. So any non-trivial homology we prove has to live inside this trapezoid. Oh, I'm sorry, I didn't tell you how we're normalizing. We have 4 parameters, but the x-axis is going to be n over pq. In other words, the volume fraction that the squares take up, the area ratio that they take up. So again, like a stand-in for pressure. And then now we're going to normalize j, the degree of homology, the same way by dividing by the area of the square. Okay, so that's how we normalize. We show that only non-trivial homology can be inside there. And we show that first we show a homotopy equivalent cubical cell complex, and then most of our paper is doing discrete Morse theory on that. But then we also show that for any point inside this bounded by this parabola and this dotted line and this line, there exists non-trivial homology for large enough in pkj. And then blue dots are actually small examples we found for like n up to 6. And we have some reason to believe that the right answer is that that parabola and y is, so we think that y less than or equal to x can be improved to y less than or equal to x minus 8/9 x squared, this parabola, that there's nothing up here in this corner of the trapezoid. And then we also believe that 1/3 can be improved to 1/4. So that's our main conjecture in the paper is that, this is our main theorem. It's sort of summarized by that. And there's a partial converse to this saying that, as long as these, more or less, as long as these are satisfied, that for large enough, if we fix x and y, then we can find NJPQ so that there is non-trivial homology for any rational point inside that region. So we think that's the right answer, but we can't prove it. So just to comment about where some of these non-trivial cycles come from, you can imagine doing something like this, here's a circle, a circle, and a circle, but then we can also nest, the movements, this 2x2 square sliding along with this 2x2 square moving around in a big 2x2 grid. So composing all those, we have a 4-dimensional torus, but using only 6 squares in a 4x4 grid. That is this point right here. X is 3/8 and Y is 1/4. And we think that's like an extremal point, and that you can't get further out into this corner. Like that kind of nesting trick is the only trick we know. So that's all I had to say today. But given the audience and what you guys talk about in this seminar, sometimes I think, but we don't know anything about topological complexity of Farber or LS category of the, what about other kind of homotopy theoretic invariants, and especially like, maybe it would be interesting even to approximate those things for large ends, to have meaningful bounds. I'd be really interested to hear anything about that. So thanks again for your time and attention, and for the opportunity to give a talk. I'm happy to entertain any questions or comments anybody has.
Well, thank you very much. Please, everyone, if you could open up your microphones and join me thanking Matt for this great talk. So as Matt said, we're open up for questions from the audience, if you have any.
So I would have 2 questions.
Go ahead.
The first is, what can you say about the unordered case? And the second is relative to the last picture with the parabola that you showed us. If you can pick it again.
This one?
No, the previous one.
Yeah.
Yes, this one. So one thing that I noticed, maybe you also saw it, there seems to be an empty wedge in the bottom of the picture. There's the line y equals 0 where there are dots, and then there is an empty wedge in some.
Like this little
Yes,
wedge?
Exactly.
Right.
Do you have an explanation for this? This is the or an idea of why there could be such a wedge.
Yeah, I think it's just because the only points that we've plotted are up to n equals 6, and as n gets bigger, so we can prove that for any point, including all the way down near this corner, if you fix the point xy, then there exists njpq such that hj configuration space of n squares and a p by q rectangle is non-zero. In fact, even you can make p equal q. But you may have to make n larger, to get down into this corner. So I think, yeah, this is just n. It might not even be n less than or equal to 6. All these dots might just be n equals 6 as j and p and q vary. And so I think that this, I would have to think it through, but I think this wedge being empty is just an artifact of small n. But your first question about, what happened for the unordered configuration space is an interesting one. And with that discs in a strip paper, we just got back a referee report. And the referees were generally positive, but one of the referees said, I think you should write something about the unordered configuration space. And I think you probably could with the methods that you already have. And it's probably physically relevant to do that, right? Because the physicists might not distinguish different particles. It might be actually more physically meaningful to talk about the unordered configuration space. So, but we got into it, and the answer ended up being more complicated than we thought. So I think for disks in a strip, we can completely I'm not sure if we'll be able to completely say what the Betty numbers are or not, but I think we can probably say what the asymptotics are. So like one fundamental thing about the asymptotics though is that the Betty numbers never grow faster than polynomially fast. So you don't get that exponential growth anymore that you do for ordered configuration space, but you're comparing it to something different. The configuration space of points, the unordered configuration space has Betty 0 equals 1 and Betty 1 equals 1, and all the higher Betty numbers are 0. So the Betty numbers are really small or almost trivial for the unordered configuration space. The thing that's really interesting for the unordered configuration space of points in the plane is torsion in homology. I'm not sure, but I think this was first worked out by Fred Cohen in his PhD thesis, maybe the homology, the integer homology configuration space of points in the plane. And that would be really, we don't know whether there's like any extra torsion or not. That would be super interesting. But even the Betty numbers, they do grow for the unordered configuration space of points. We know that, and we know they don't grow faster than polynomially, but there's some weird things that happen. Like all of a sudden something depends on whether the strip is even width or odd width. And that it just ends up being a more complicated story. So I think we'll try to write this in a future paper, but the short answer for now is like, we don't know that much. And we haven't even really started to study it for hard squares in a square, what happens for the unordered configuration space. But like another reason to study the unordered configuration space is these cell complexes are a lot smaller. I mean, divide by n factorial, the number of cells. So like a lot smaller, and we could do more computations and, get more experimental evidence from small numbers of particles. So there's lots of reasons to study unordered configuration space. It seems a very natural thing to do.
Are the hard squares in a square k pi 1 spaces?
They're not in general, but we wondered this, and it's a great question, especially because they're cube complex, so we could use Gromov's criterion, but we don't get that lucky. The link of a vertex isn't flag in general. So I think so there's one case where we do get new k pi 1s though, for disks in a strip. When the width of the strip is only 2 disks wide, when W equals 2, the cell complex that we look at, the subcomplex of the Salvetti complex, ends up being a cube complex, and it satisfies Gromov's criterion. So we get this new k pi 1, and it's that was exciting to us. That but like we also know, it's not ever a k pi 1 for like width 3 or width 4. It's just width 2. It's something special that happens there. So I looked into this a little more, and so like a related space that's been studied before is the no k equal configuration space, right? Like Bjorner and Welker, a bunch of people studied this. Like just take points on the line, and you can have 2 points like touch each other, but maybe you can't have 3, say, or in general, you can have k, but you can't have k plus 1. So and you could do that for reals or complex, and both have been studied. So I think the no 3 equal for on the real line, Bjorner conjectured that that's k pi 1, and Kavanagh proved it. And Kavanagh described it as like it's a real analog of the fact that the no 2 equal complex configuration space, in other words, the configuration space of points in the plane, is a k pi 1. He should no 3 equal, real configuration space is a k pi 1. And our configuration space of n disks in a strip of width 2 maps to the no 3 equal configuration space of Bjorner and Welker. Like you just forget the y coordinate of the disk, and they all, and where the strip width is 2, so you can have 2 disks with the same x coordinate, but you can't have 3. So it just maps, it projects down to the no 3 equal configuration space. And one thing that's funny is like they seem to be related, like the H1 homology, the Betty numbers actually agree, but the higher homology doesn't agree. And we make a comment about this at the end of our paper, that there seems to be some weird connection between these different k pi 1 spaces that we can't explain. That the n disks and a strip of width 2 and the no 3 equal real configuration space. But yeah, so far we haven't found any other k pi 1s in this whole study of configuration spaces other than that one.
Matt, regarding to your very last question about topological complexity and related invariance for these spaces, I I understand from what you said that there is no torsion in the homology of these spaces. So you would immediately have a hand on the cohomology. And the question is if you have worked out multiplicative structures on the cohomology of these spaces or some more related structure.
No, it's a really natural question, but we haven't looked at any product structure. Oh, so no, not really. We don't know, like, say, anything about the product structure of cohomology, and that would be really nice. Well, so if this is what you're getting at, for example, then there might be cup length bounds on TC or category of the space. But this work in progress by Hannah Alpert and Fejia Manin, there's this twisted algebra structure, but there the product is, something funny, like where you're relating the configuration space of n disks and configuration space of m disks with the configuration space of n plus m disks. And you can do that in disks in a strip by just putting them next to each other. There's always room to do that, but that's a really different kind of product than just, the cup product in cohomology. So we don't know anything about it, and I think it would be really interesting to study. Did you have a question too, Erica?
Yes, thanks, Matt. I think I've never heard an answer to this question, and I have been holding it, but is it expected that when we look at 3 dimensions, that where is actually like phase of transitions of matter happening, that our understanding of in the plane, everything in the plane, will lead us to a natural understanding of what actually is happening in 3 dimensions? And in particular, I don't know of any sliding puzzle in 3 dimensions, but that is because we cannot actually play with it. But I've always wondered if actually studying this and understanding this will lead us to 3-dimensional understanding of the same phenomena.
So I'm not sure if I understood your question. Are you saying will understanding 2-dimensional phenomena help us understand 3-dimensional phenomena better?
Yes. Yep.
I mean, I think that's the hope. That's one thing that I like about these suggested definitions of homological, solid, liquid, and gas, is that they're quite general. You could have any shaped particle inside any ambient configuration space, and it always includes into the configuration space of points, So if you have an isomorphism on homology, then they sort of look like point particles. So we sort of expect the same qualitative kind of behavior in 3 dimensions as we do in 2 dimensions, but it's just, yeah, I think we could prove things about, like, if disks in a strip in 3 dimensions is like 3-dimensional balls between 2 planes, then at some point Bob told me that there's a spectral sequence that relates the homology of disks in a strip of width 2 to configuration space of balls and R3 between 2 planes. And so actually the hard case, and you could do it in higher dimensions too, the hard case is disks in a strip in the plane. That's what you need to start the spectral sequence calculation. So at least that's what Bob told me. And but yeah, but just for like simulations, like cubes in a cube or something, computing small examples in the 3-dimensional cube might be interesting and might be rich. The examples are going to get bigger faster in 3 dimensions than they do in 2 dimensions. Yeah. So we might not be able to go quite as big, but again, that's an argument for the unordered configuration space though. What about divide everything by n factorial and then your quotient, your cell complex, so you have something smaller to compute with. I think some experiments would be interesting. Jeremy Mason, by the way, is studying these things experimentally in 3 dimensions now, trying to understand the topology of the configuration space of like n balls in a parallelepiped, say, or a torus, and a 3-dimensional torus. And he's telling me things that I had trouble believing, but might be, like that with like maybe 3 balls and a parallelepiped in a torus in 3 dimensions, that the topology changes many, many times as the radius of the balls varies. like that they found like 40 or 50 different critical points. And, you know, it sounded unbelievable, but that there was like lots of different ways the balls could be tangent to each other. So,
and that would be similar to like analyzing square configurations in polyominoes with some homology, perhaps.
I'm not sure. It might be. Yeah, you can also make the ambient, you know, thing that they move through more complicated too. That's I'm not sure if what else we get extra like physically or mathematically out of that, but it's certainly, you know, a reasonable question. You know, what happens if the squares are moving in some other shape than in a torus or in a square or in a strip or something.
Okay, yeah. Thanks, Matt.
Thanks, Erica. It's good to see you.
Good to see you too.
All right. Well, I think there's no more questions. Well, if anyone has any other question, we can just hang around to ask them. For the time being, we can stop the recording. So Dan, if you could stop the recording, please.